All right, we're going to talk about quantum numbers and how we can get some information out of them and how we can use them to represent some pictures of electron density. So the wave equation, or the Schrodinger equation, h psi equals E psi, where psi is what's called the wave function. The wave function is the solution to the wave equation. It's a differential equation, and that wave function, and there's an entire set of them, will define the energy and spatial distribution of the electron. It gives us whole number values for the energies, just like a standing wave. So we have fixed whole number values for the energy. This leads us to the n quantum number, called the principal quantum number, Qn for quantum number. This is the same as the Bohr energy level. This is the same n that Bohr used in his model. Now its values are 1, 2, 3 up to infinity, the same as Bohr's. At least that's consistent with his picture. It's primarily accountable for the energy that the electron has. And it's roughly proportional to the distance away from the nucleus. Again, similar to the Bohr model. The bigger the value of n, the further from the nucleus. And again, we don't use words like shell or subshell anymore. Energy levels only. So we also get whole number values for the angular momentum. Now the angular momentum also contributes to the energy here. But the biggest effect it has on it, and this is the L quantum number, angular momentum quantum number, the biggest effect on it is how it affects the shape. So its values are determined by the n level. We have 0, 1, 2, up to n minus 1. And again, it contributes to the energy, but you can say that it's mainly responsible for how the wave function looks, say in a three-dimensional plot. It's like where, it sort of determines the region of space occupied by the electron. Again, I keep writing this down because this is a property of waves. Whole number values for the spatial orientation. We have a fixed number of ways that the wave function can be oriented in space. And this only makes sense in a magnetic field, which gives you an environment where there's a difference between one end and the other. Otherwise, there is no difference. So m sub L, the magnetic quantum number, can have values based on what L is, from minus L up to plus L. So again, it determines the orientation of the wave function in space, in a three-dimensional space. And if you like to think of x, y, z coordinates, that's fine. They're usually defined in r, theta, phi coordinates. Okay, now the electron also has something called intrinsic angular momentum. Now, in the classical world in which we live, we call that spin. That means it rotates on its own axis. This is not classical for an electron. And again, that's because once you've defined it as a wave, it's not a particle anymore. It doesn't have an axis. It doesn't really spin. But it does have this property that we call spin. Its values are plus or minus 1/2. And that gives us m sub s, the spin quantum number. So you can have spin up or spin down. All right, here's some examples of what these might look like, what combinations these might look like. So for n is 1, you can have L is 0 and m sub L equals 0. We can have a wave function that we'll call psi 100, and this will have, say, a lot of electron density in the center near where the nucleus is, and then it will be distributed out from that. A roughly spherical sort of shape. This is called an s orbital. So if L is 0, corresponds to an s orbital. The letter s comes from the spectroscopic series, the Sharp series. Again, it's an antique word. An orbital is synonymous with wave function. An orbital is a one-electron wave function. We tend to use the word even if there's 2 electrons in it, but an orbital is strictly a one-electron wave function. So all s orbitals are spherical in shape. All right, so n is 2. L can have values 0 and 1. M sub L for L is 0. M sub L for 1, -1, 0, 1. Notice that there are 3 of those. There's 3 possible orientations. That means 3 possible orbitals, or 3 wave functions. So psi 2, 0, 0. This would be the s orbital, right? There's electron density in the center, then there's sort of a gap. There's what we call a node, just like we saw with the standing waves, right? Then there's electron density again. N minus L minus 1 will give you the number of radial nodes. So you can draw a picture of this correctly. So density in the middle, then there's a gap, then there's more density. And again, that is a picture of 1 electron. Psi 2, 1, 0. So now L is 1. That gives us a shape that's sort of this elongated kind of dumbbell shape. It has no radial nodes, but it has what are called angular nodes. And again, most of the density is in toward the center, but it has this electron density above and below that xy plane. That's called a p orbital. All p orbitals look like that, or roughly like that. P comes from principal, again, the spectroscopic series, the principal series. There are always 3 p orbitals. So let's see if we can get the pictures of these. These are the 3 different ones we could have. 2, 1, 0, 2, 1, 1, 2, 1, minus 1. Now I'm drawing them with just these smooth lines now to make it easier. These are sometimes called probability surface plots. So you can see how there are these 3 different orientations on these 3 different axes in 3-dimensional space. And you can call these PZ, PX, and PY if you like. And again, p orbitals, regardless of what the n level is, if it's a p orbital, there are always 3 of these. They might look a little different depending on their energy. All right, let's try n equals 3 now. So we can have L is 0, and 1, and 2. M sub L values for these. For L is 0, it's just 0. For 1, again, -1, 0, 1. And for 2 now, -2, -1, 0, 1, and 2. There are 5 of those. Let's take a look at the s orbital, 3, 0, 0. How do we know it's s? Because L is 0. N minus L minus 1, to see how many nodes, how many gaps you have to make in it. There's 2. So electron density in the core, or in the middle of this thing, another region of electron density around that, and then a third one around that. So that makes 2 nodes. And I'm going to keep saying this. That is a picture of 1 electron. 1 electron, and it's distributed in that way. So 3, 1, 1. This will be a p orbital. How do we know that? Because L equals 1. N minus L minus 1. We have to account for 1 radial node in a p orbital. It takes just a small amount of drawing skill. It's not that tough. I'm going to do the same dumbbell shape, but it sort of is cut through the middle like that. There's a radial node in it. So this is what an n equals 3 p orbital would look like. Again, distributed in that same sort of dumbbell shape, but with a radial node. And there are 3 of those. I'm not going to take the trouble to draw all 3 here. All right, so these are the ones we could have for the L equals 2 orbitals. 3, 2, 0, 3, 2, minus 2, 3, 2, minus 1, 3, 2, 1, 3, 2, 2. So these are called d orbitals. D, it's from diffuse spectral series. There are always 5 of these d orbitals. Again, no matter what the n level is, the d orbitals within that n level, there's always 5 of them. So these have this sort of clover leaf shape. At least 4 of them do. The 5th one's a little bit different. And they are oriented, so these would correspond, what I'm drawing is the different m sub L values, right? These are all d orbitals. I'm trying to fit in all their different m sub L values here. And you can see that they're oriented along different axes. That's what makes them different from one another. And the thing to remember, I haven't emphasized this yet, is that all of these orbitals exist simultaneously. They're all superimposed on top of one another. You draw them separately so you can see them, otherwise it's just a big mess. You can see how these are oriented on the different axes. There's 4 of them. I ran out of room to draw the 5th. You got 1 more to do. In case you're curious, this one's called the dz squared orbital, and it has unusual symmetry as compared to the other ones. Most of the density is like that, and it has this sort of little torus of distribution around the center. That's the dz squared orbital. And again, all 5 of those exist simultaneously, as do all the p orbitals, as do the s orbitals within that one atom. They're all piled up on top of one another. So every orbital can be occupied by 2 electrons. And we use the word occupied as if it were a space to put an electron in. That's perfectly okay. It's not exactly physically real, but it's a perfectly useful thing. You can fit 2 in there if they have opposing spins. So if we look at how many we could get in a given n level, for n is 1, we can only have 2 in there, right? For n is 2, we get 8. For n is 3, we can fit 18 in. For n is 4, we can fit 32 in. We can keep going from there. Now you can sort of account for where these are located by doing this. There's 2 in that 1s level. In this one, we have a p level, right? There's 6 in that. In n is 3, we have s and p and d. You can see how they all fit in. Again, why is there 10 in d? Because there's 5 of them, right? 5 times 2 is 10. And here, with level 4, we can have an f orbital too. There are 7 of those, 14 electrons in an f orbital.